We've got coming up next our afternoon contributed session, and the session chair will be Nicola Morlica. So let me pass the baton to her.
Thank you, Aaron. So just a quick check, can everyone hear me?
Yes.
Great. So we have a wonderful afternoon session. This first speaker is Lee Cohen. Lee, can you please share your slides?
Sure. Do you see and hear me?
Yes.
No, just see the slides. Yeah.
That's great. So also just as Adam did in the morning, I'll be asking everybody to keep their own time, 5 minutes for talks, and then we'll have some discussion afterwards. And this will, you know, it's just hard for me to give you timing signals, but I'll cut in if you're going way over. So thanks. And so now our first talk is by Efficient Candidate Screening Under Multiple Tests and Implications for Fairness by Lee Cohen.
Thanks, Nicole. I'll start by describing the motivation. Consider an employer that would like to hire candidates for jobs. Of course, she's only interested in the skilled ones. We assume that there is an infinite stream of candidates from the same group, and that each candidate, I, has a binary skill level, which is sampled from a Bernoulli distribution with a known parameter P and remains permanent. So each candidate is either skilled or unskilled. Now, the problem is that, given a candidate, the employer cannot observe his underlying skill level. Instead, she can only estimate it by performing a series of tau binary tests or interviews, which gives her a noisy feedback. So each test is either pass or fail. We assume that tests are conditionally independent given a candidate's skill level, and that all the tests of all the candidates from the group has a fixed probability to flip the candidate's skill level. We look into two types of policies that decide whether to hire someone. We start with the threshold policy, which has a fixed number of tests per candidate, and accept candidates that pass at least theta out of tau tests. What about the objective? So, if we think like an employer, we would like to find a policy that minimizes the false discovery rate, the fraction of unskilled candidates accepted by the policy. And of course, we need to add a constraint, or else the policy would simply reject everyone. So we require that the expected number of tests per hire would be lower than a budget parameter B. We show that the optimal policy for this objective always exists. But apparently, there are some group and budget parameters for which the optimal threshold policy does actually something rather stupid. It rejects candidates that are more likely to be skilled than any other freshly sampled candidate from the pool. The problem is that if we change the policy to accept these candidates that seems better than a freshly sampled candidates from the pool, we increase the false discovery rate because these candidates are not there yet. So the solution will be to keep testing the candidates whose posterior probability is better than to be skilled is better than untested candidates. This brings us to the second type of policy, the dynamic policy. The dynamic policy decides after each test whether to accept, reject, or keep on testing. Now, turns out the intuition we had in the previous slide was correct. The optimal dynamic policy is in fact greedy. That means we should keep on testing as long as the posterior probability that a candidate is skilled is higher than the probability of a freshly sampled candidate to be skilled. And when this posterior probability achieves the desired full discovery rate, the greedy policy accepts the candidate. We showed that the greedy policy minimizes the expected number of tests under the false discovery rate constraint. So this is indeed the optimal policy. We also have similar results in case we want to keep a low false omission rate, which is the fraction of skilled candidates rejected by the policy. In order to analyze the problem, we reduce it into a one-dimensional random walk. Now let's see what happens when we add another group of candidates. So consider two groups with the same fraction of skilled candidates, but different noise levels. One of the groups has a higher probability for a flipped test result or interview result. Now, impossibility results emerge for both types of policies. Candidates from the group with the higher level of noise suffer from higher false negative and false positive rates. In addition, since unskilled candidates are hired, they are more likely to end up being fired. So it is more likely that candidates from this noisy group would end up being fired. Later on, employers might erroneously conclude that this group's average skill level is lower than it actually is. So we propose to fix this by using the dynamic policy. How come? We would give more tests to the noisier group. Together with the random walk analysis, we can adjust the false discovery rate and the false omission rate to achieve the same false positive and false negative rates between the groups at the cost of giving more tests to the noisier group, and we know exactly by how much. Thank you very much.
Thank you for the talk. We have some time for questions. So you can either raise your hand or if you're a panelist, you can just unmute yourself, or you can type questions into the Q&A or the chat. I'll try to monitor all these channels simultaneously. In the interim, I was curious, so it seems like your technology requires the sort of disadvantaged group to take more tests, which itself might feel like a bit of a disadvantage. And I was wondering if you have any results about that, or perhaps,
right.
Yeah.
Right, that's a good question. So the noisier group is indeed paying and would end up having to do more tests. But this solves this issue of higher rates of firing from this group and low estimation of the group's skill level. And in addition, we also know that that the skilled candidate among this group would be the ones that would end up going to and start a session of interviews. So we can do more work in the area and maybe even consider a stackable equilibrium and see where this leads us. But we believe that only the skilled candidates from the group would start the testings. Would go to the job to interview.
I see. Okay, thank you. It might also be interesting to see what you can do with a limited number of tests. Like if you're not allowed to test some participant more than some number of times, does your policy automatically bound the testing?
So you could add a limited number of tests, but it would you would add certain limitations. And of course, we also have the analysis for the fixed number of tests, no matter what is the core parameters of the skill level and the noise.
Yeah, okay, thank you. Pragya, you can go ahead and ask your question.
Yeah, hi Lee. So my question was, I was wondering, you control the FNR, FPR, these sorts of error measures here. So would your proof techniques extend to like other forms of error, such as like FWER, which typically controls that the probability that you make at least a wrong decision is that it's bigger than equals 1, some kinds of bounds on that probability? Like as opposed to expectation. So FNR, FPR are sort of expectation over quantities, right? So it's like average control over sorts of errors. So as opposed to, so FWER will be like a tail control, like probability that you make at least a single error. That's the quantity. So I'm just wondering whether your proof techniques can extend to control such sort of tail probabilities along with the expectation.
So right now the answer is no, but in fact we also have a Gaussian model, which you can analyze by using the Brownian motion, and then you might achieve that.
Nice, thanks. Okay,
Thanks so much for your talk, Lee. And I guess there's one more question, which is from Ron Smartinsky. How about introducing incentives, perhaps by adding a cost to apply for a job? This may result in some self-selection and possibly flesh out the forces pointed out in Ricky's talk. What do you think?
Yeah, this could be a very interesting future work direction.
Yeah, okay, I think
we actually had this in mind, but we haven't developed it.
Okay, interesting, thank you. I think we'll take further discussion offline, and can you please stop sharing your slides? And Pragya, I believe, is the next speaker. So if you could start sharing your slides. And you need to unmute yourself. Or I can unmute you maybe.
thanks.
Yeah,
My
great.
unmute button just decided to vanish right at this moment.
No problem. Next talk is Pragya Sur from Harvard University, and she will be talking about abstracting fairness, oracles, metrics, and interpretability.
Okay, thank you. This was joint work with Cynthia Dwork, Christian Elvento, and Guy Rothblum. So in this work, we begin by arguing that context is absolutely crucial for fairness. Now, several fairness definitions can be described using two interacting components. Typically, there is a technical condition that's part of the definition, which comes with a context or auxiliary information which you need in order to determine whether your classifier satisfies the particular definition. As examples, you can think of metric fairness, where the technical condition is a Lipschitz condition on the classifiers. And the context is in the form of a metric, which determines which individuals are similar to which others with respect to the particular task at hand. Moving on, you can also cast multi-calibration in this setting, where the technical condition is in the form of a calibration condition, and the context is in the form of a collection of sets with respect to which you would like to have your classifier to be calibrated. And actually, there are several other such notions which can be cast in this setting as well. Counterfactual fairness is one such notion, which comes in the language of causal inference. The technical part says counterfactuals should be treated similarly, and the context is in the form of a causal model that needs to be fully specified. And these counterfactuals are also evaluated with respect or determined with respect to this causal model. And this list can go on. So basically, the summary is that context is really crucial in all of these cases, and generally context is crucial for fairness, and different contexts can lead to different conclusions. Such arguments are made even further in a very nice way in this wonderful work by Baer et al. So if we think of such fairness definitions, so let's fix the task and let's call W to be such a generic fairness definition of this form. Then in order to operationalize it, you will need to have side information regarding which context is appropriate. In this work, we model such side information as coming in the form of an oracle who understands the true context, okay? We don't know how it understands it, but it has some understanding of the true context. We are allowed to interact with this oracle in the following sense. So we can feed in context classifier pairs that satisfy this definition into the oracle, and the oracle simply outputs an accept or reject, 1 or 0, based on some true understanding of fairness, which is likely governed by its understanding of the true context. And of course, this is an oracle. We don't know how it functions. It just gives us this answers in these bits, 1 and 0. What we ask in this work is, what is it that we can learn from such oracles? If it helps visualize, you can think of the oracle as a human expert who understands functional relationships between the variables that are involved, but is unable to enunciate them, just says yes, no. We find that we can learn a surprising amount from such oracles. And in this work, we produce extraction algorithms that by interacting systematically with such oracles is capable of recovering the truth that the oracle holds, and for some instantiations of the oracle recovers approximations, good approximations of this truth. And this is applicable for any fairness definition which takes on the form that I described before. And what ends up happening is that our algorithms end up producing a coarse metric on the space of individuals in the universe, which can further be enriched using the threshold combination procedure by Vento. This is the subsequent part of the work in the subsequent talk to create better metrics when you use a sequence of such oracles. Okay, so the main summary is that we have these explicit extraction algorithms which are capable of recovering the truth. So then what do all of these imply? As we started by arguing, fairness definitions need to incorporate context for the particular task and the social setting one is employing the task in. Now, then we saw that this need to reason about the appropriateness of a given context is then crucial if you need to incorporate context. And this ability to reason, which we formalize as an oracle, our extraction algorithms imply that this means one has some coarse notion of a metric, or the oracle has to function under a coarse notion of a metric. In turn, this ends up connecting seemingly unrelated notions of fairness, because the notion you started with may not have been metric fairness. And finally, our work also has has implications for interpretability, which allows a human arbiter to reject classifiers when he or she deems it to be unfair, because the way our oracles are framed could be viewed as such human arbiters, in which case, once again, our extraction algorithms imply that the arbiter has to be functioning under some notion of a metric. Our algorithms are inefficient, and we hope that this is going to inspire more work in the future directly on metric learning, or developing efficient query models for interacting with such oracles in settings where that is possible. Thank you.
Thank you. So again, please ask questions either in the Q&A, in the chat, or in the participant list by raising your hand. So we have a question from Aloni Cohen from the Q&A. Can you clarify the connection between the extraction algorithm and the metric? Are you saying for any oracle there exists a coarse metric relative to which the metric fairness implies oracle fairness?
Yes, so that's a great question. What we are saying is, under the particular setting we are in, the oracle just gives us 1-0 answers, and using this interactive system where we are allowed to feed in such pairs, context classifier pairs, which satisfy the definition, from just this 1-0 answers, we are able to extract the truth from the oracle. And it ends up happening that the truth is in the form of classifiers on the space of individuals. which itself form coarse metrics. So we don't really know how the oracle is functioning. It just tells yes and no. The point is this explicit extraction algorithm is in some sense an existence proof that we are able to extract the metric from such oracles is an existence proof that the oracle has to be functioning under some notion of who's similar to whom.
So Aloni Cohen says, so every definition that fits in your model is a special case of metric fairness?
Again, that's a great comment. I wouldn't say describe it as a special case. Let's take an example. Suppose, counterfactual fairness fits in that setting. And what this means is counterfactual fairness requires a context that's in the form of a causal model. On the surface, it seems this is very different from metric fairness. But through this procedure, you are establishing that in some sense, learning the true causal model is related to learning a metric. So in settings where you're unable to learn the true causal model because that just requires too much information, you could instead invest in learning metrics or developing such query models if you have access to such oracles. So I would say it ends up connecting seemingly unrelated notions through the fact that learning the context for one, in some sense implies you have to have a notion of a metric. That's what our result establishes. So then you can choose whichever is harder. You don't need to do that in that setting. And you can instead build like efficient query models where it's feasible.
So we also have a question from someone that raised their hand, Salil Vadan. I have allowed you to talk now, so you can ask your question.
Hi, Pragya.
Hi,
Can you say a bit more about what you assume about the oracle? I mean, it gets a context and a classifier as input, but it also has some true context. Under what conditions is it required or supposed to accept or reject?
Right, that's a great question. So, okay, what we assume on the oracle is the following. The oracle, so there is a set of context and classifier pairs. We have two versions of the oracle. In the simplest version, we call it the strong oracle, which has a set of context classifier pairs that it accepts and it rejects everything else. So this is the simplest case. And whatever this oracle accepts, let's call that set, a set tau of context and classifiers. We just don't know what gives rise to this set. So it could be that the oracle understands the true context and believes in some notion of fairness, and it's evaluating every classifier with respect to this true context and is happy whenever a classifier along with some context satisfies this definition. It could be that, but we just don't know. So this oracle gives rise to a set of context classifier pairs. But then our main result is for a weaker version of this oracle, which we call weak oracles, where the weak oracle is every weak oracle is associated to a strong oracle, and a strong oracle is associated with such a set. But the weak oracle doesn't tell us 1, 0 for all such pairs. So it looks at as the inputs we are feeding in. And if the classifier is really far from anything in this set the strong oracle believes in, then it says reject. And for everything else, it behaves arbitrarily. So it's in some sense like a promise problem. So it has some set it believes in. Everything that's far from that, it rejects. Far is defined in some terms of certain distances. And everything that's nearby, it just behaves arbitrarily on that. So it's allowed to bake in whatever true fairness it believes in. So there's a lot of flexibility there. Yeah.
Okay, thank you. I think in the interest of time, we'll move on to the next talk. So if you could stop sharing your screen, and then Christina, I believe you are the next speaker, so you can take over. Awesome.
All right, let's see if I can appropriately share my screen here. Okay, do you see slides?
Yeah. Yeah.
A slide. Okay, that's all we needed. Okay, so thank you, Nicole. I'm very lucky to be speaking right after Pragya because she's already done the hard work of explaining what individual fairness and metrics are for me. But just to briefly recap, individual fairness states that similar individuals should be treated similarly. And to capture similarity, we assume the existence of a task-specific similarity metric, D, which captures society's best guess of who is similar to whom for a particular task by providing a distance between each pair of individuals. So once we have our hands on this metric, we say that a randomized classifier is individually fair if the difference in treatment for any pair of individuals is no more than their distance in the metric. And as a fairness definition, this has very strong properties. So first, every individual is given a guarantee on their treatment with respect to all other individuals. And in terms of the perception of fairness, this is really important because it treats individuals' context with care and nuance. It can be difficult to confirm from group-based statistics alone that individuals are really being treated fairly. And in some sense, group-based definitions allow us to justify bad treatment of one individual or a subset of a group by saying that we treated someone else in their group really well or someone else in a different group really poorly, which doesn't make much sense from the perspective of that individual. So the other really nice thing about specifying fairness in terms of a metric rather than statistics is that it allows us to think about fairness separately from accuracy or the objectives of a specific classifier and to explicitly make space for human judgment. Okay, so this all sounds really, really nice. So why aren't we using it in practice? The problem, of course, is how do we get our hands on the metric, which is the goal of this talk. And just by way of like a little bit of context here, because you just heard Pragya speak about metrics based on oracles, that talk was very much in the abstract. And here we're going to try to bring the problem a bit closer to really asking human beings, real questions to try to get our hands on this metric. Okay, so we're going to assume that we have access to a fairness source of truth, and that source of truth takes this form of a human fairness arbiter. And so these people are individuals who we assume are free from explicit biases, motivated to engage ethically and honestly in our query protocol, knowledgeable about the task at hand and any relevant historical or cultural context, and able to answer well-formed questions about similarity, but we won't ask them to justify or explain their answers. Our goal here is essentially to construct a metric that our human fairness arbiters agree has small distances between similar individuals. So we're not really trying to get our hands on some complicated latent metric that the arbiters have in their heads. We're really trying to come up with a set of distances that the arbiters agree aren't pulling similar individuals too far apart. Okay, so how do we do this? Well, the first thing that we do is we define an approximation to the metric. And as I just said, fairness only requires that we don't pull similar people too far apart, but it's fine for us to underestimate distances. So we introduce the notion of a submetric, which mostly underestimates differences, but is allowed to have some small additive error. And once we have this approximation notion in place, the second question is, how do we actually ask our human fairness arbiters who is similar to whom? And so we'll consider two types of queries. The first is a relative distance query, like is A closer to B or C? And these are generally pretty easy to answer. Like we can see these two lines, one is clearly longer than the other. The second type of query is real value distances. And this is a lot more difficult. Asking an arbiter to tell you like a distance between 0 and 1 for A and B is not as easy as asking, who's closer. And if we just take this query model like at face value in the abstract, we could imagine a really naive solution in which we ask the arbiter n-squared real valued queries to discover or recover the entire metric, but that's really unrealistic. And a significant part of this work is showing how we can replace hard queries, so not doing n-squared real valued queries, and instead using a smaller number of easy queries. And loosely speaking, we do this by choosing a representative element, for example, D, and then generating an ordering by distances from that element using easy queries, and then layering on distances at a given granularity using a much smaller set of those harder queries. Obviously, we lose some distance information for pairs of individuals who are equally distant from the representative when we do this. So we also show how to merge distance information from multiple representatives to preserve more of that information. Okay, so this is a 5-minute talk and I'm already over 5 minutes, but to entice you to read the paper or watch the longer talk video, there are a few other things that we do. So we show good strategies for choosing these representative elements, how to generalize the submetrics we learned to unseen individuals. We also show how to relax the query models. The arbiter doesn't have to give precise answers. They can say they don't know or answer with a bit of noise. And then some additional discussion on the modeling choices. And with that, I will try to make Nicole's job easy and wrap it up. So if there are any questions, I'm happy to take those now.
Thank you very much. So any questions? Again, you can type them into the chat, into the Q&A, or raise your hand in the participant panel. I'll be monitoring all three of those technologies.
Can I just butt it?
Yes, you can also just butt in. Go ahead.
So these arbiters, so how do you imagine presenting a description of the individuals to the arbiters?
Right, this is a great question. So what does this interface really look like? And I think that this is one of the open modeling questions that's very important. So in some sense, I would anticipate that the data that's presented to the arbiters would probably be a lot richer than what we would normally think about for like a machine learning system. So one example that I would think of that might be like helpful to keep in mind is something like an admissions committee for college. Obviously not a perfect system, but you have a group of dedicated people who understand the context of the problem that they're evaluating, and they actually take a lot of time to read the application, the essays, the recommendation letters, look at scores if it's appropriate, interview the candidate if it's appropriate, that you would have a very rich set of information. I think the challenge here, and this is something that we talk about more in the paper, is that's probably what you want to do with your arbiters, is really give them a full view of each of your candidates. But in practice, you might have a much smaller set of information. So the challenge there is taking potentially like a large investment you made with arbiters on a smaller sample of individuals and generalizing that out to potentially less information for unseen individuals. And so I think Pragya mentioned this before. The technique that we use there is to learn threshold functions. So rather than trying to learn something complete, we'll learn things at thresholds and then round down. So we'll get something that isn't totally faithful to the original metric, but it is trying to pull people closer rather than push them further apart. Does that answer your question?
Yes, thank you.
Yeah, I think the model choice here is definitely non-trivial. So I really encourage you to read critically or watch the talk critically. I don't think by any means that it's settled how we should be looking at these types of questions.
So we have a question in the Q&A from Catherine Yo. What is the best way to select the arbiters to be on the committee?
So I'll tell you probably the worst way to do it, which is to have whoever is writing the code select them. So I think this is really, so who gets to be an arbiter is critically important to whether or not anyone believes that the metric that you're learning is even close to approximating fairness. So I think that the selection procedure for arbiters is something that is more social, and I don't want to say political in a bad sense, but political in the sense of we want people involved in the process. And that procedure of how we should choose arbiters, how we should handle disagreements between arbiters is something that, you know, it's certainly important for us to have some influence on that and to explain what the technology can and cannot do. Can you add and remove arbiters easily? Can you prioritize them easily? But that's something that I think makes a lot more sense for domain-specific experts to say more about than, you know, for me to say anything about. I hope that isn't a total dodge, but I want to also be really clear that, like, I should not be telling you who your arbiters are.
Thank you. There's one last question and then we'll move on to the next talk. This is from Michael Yang. How directly interpretable and or simple are the learned metrics from arbiters?
That's a great question. So I think there's a question of how, like, whatever technology you use to learn the threshold functions and combine them, you could say something about that. I don't want to be too prescriptive about what technology you use there. One thing that's nice about arbiters, so for example, if you have two arbiters and you ask them the same question, they disagree, well, you have the question that you asked them, and you have the two people or three people, if it's a relative query, that they disagreed on. And so I think that in some sense, I'm not sure that interpretable is the right word, but in some sense, there should be a good paper trail of what were the questions we asked, what were the judgments that came out of that, and did, you know, arbiters disagree, or everybody agreed that, you know, this was the case. So I think I would be more comfortable saying that there should be a good paper trail generated by this procedure, but I'm not necessarily sure that I would say like the classifiers themselves or the generalized metric itself would be like interpretable per se. I hope that helps.
That's great, thanks. So then we're going to move on to the last talk. So if you could stop sharing, and Kevin, you are the last speaker. So can you please share your screen? Great, so the last talk is Kevin, recovering from biased data, can fairness constraints improve accuracy?
Great, that's me, guys. Can you hear me? I'm gonna say yes. No one said no yet.
Yes, we can hear you.
All right, fantastic. Sorry about that. Thanks, guys, so much for coming. So our paper is Recovering from Biased Data, Can Fairness Constraints Improve Accuracy? And this is joint with my advisor, Avram Blum. So going back a second, we're moving away from individual fairness. We're going to do some group fairness notions. So imagine we're doing binary classification. And one response to sort of fairness issues has been, let's add some constraints to our optimization problem, and they're going to be group-based. So like equal opportunity, equalized odds, parity. And these notions are supposed to sort of, we're learning from data. The data is, maybe there's some bias phenomenon happening, but we want to sort of mitigate the harms by saying we satisfy this group notion. And that is not our perspective. Our perspective is a little different. We want to say, we want to try to learn accurate models, but from the biased data. And so kind of the key assumption we're making here that is actually quite strong is that we're saying there does exist some nice distribution with two groups that is fair, but the bias is introduced into the training data because we don't get access to that nice distribution. We get a noisy kind of muddled distribution that has bias effects introduced into it. So like maybe some groups are over or underrepresented in the population, or maybe we're getting noisy or biased labelers from like biased human labelers. And then the question is, do these fairness constraints for the group setting, do they help us recover a accurate distribution on the true distribution when we evaluate those fairness constraints on the biased data? So that's our question, and the answer is, in our setting is yes, but we sort of kind of make some strong assumptions. So here I'm going to flash you guys the classic fairness constraints and interventions we talk about. So we're going to mostly talk about equal opportunity in this 5-minute talk. So just remember equal opportunity, people were defining it earlier. So this requires that you have the same true positive rate on your two groups. So assuming we're doing binary classification with two groups in the population, group A, group B, and they're different sizes, so there's some parameter R that determines the relative prevalence in the population. So you should think of group A as the majority group, and group B are the people who are going to suffer the harms of the model. Also, there should be a comma here that says R in 0, 1. And so the way the distribution works is when you're sampling a data point X, you flip a coin with bias 1 minus R, and then that gives you which group you're in, and then there's a different distribution over features for each group. And we are going to learn a classifier for each one. And so we make some bias models, and we have a way labels are created, and then we have fairness constraints, and we want to look at the interaction of those three things. So we assume labels, we assume we have some hypothesis class H, and there exists some H star in the hypothesis class that is the most accurate classifier on the data in that class. And so there's some parameter eta, here eta is a third, that is your error of the best classifier, the Bayes optimal classifier. So the top of this classifier gets the positive classification, but with eta, there's some error on the top, and here these are negative. These get the negative classification, but eta, 1/3, there's some error. And our first kind of most representative bias model, we say with some uniform probability over all input space, positive examples from group B, they're just not going to show up in your training data. So maybe there's some kind of censoring process or some kind of filtering. And then so you're going to learn a more pessimistic classifier on group B if those people don't show up. And so this is characterized by this parameter beta. And so beta is a probability that positive examples stay. So if beta is less than 1 minus eta, you're going to be very pessimistic on group B. And equal opportunity sort of prevents this, because if you're forced to do the same true positive rate on both groups, and you're evaluating this on this biased data, in order to do high accuracy on group B, you're going to classify everyone as negative, but that's going to force you to do something similar on group A, and that's going to give you really high bias error, because group A is the majority of the population. So that's not going to be the optimal solution. So going back, our paper characterizes what the optimal solution to the constrained ERM problem is. And we say that optimal solution on the biased data has these nice properties on the true data distribution, which is unobserved. So here I'm just going to flash our main theorem really quickly. And basically, in words, what it is that if the signal is not too noisy and the majority group really is a majority, we show that equal opportunity recovers across a few different data distributions. And there's some kind of weird intuitions here, which is we make assumptions on both groups such that they have basically identical distributions in terms of how many positives for each group. But so they actually satisfy parity, but parity is not going to recover the true distribution when you evaluate it on the biased data. And kind of what is the takeaway here? The takeaway is that if you're looking at kind of your ability to recover from this biased data issue where you want to evaluate on this kind of unobserved distribution, fairness constraints can help you do that. But there's sort of separations depending on the assumptions you make in the bias model. And this recovery behavior is really tuned to the bias phenomenon happening, to the bias assumptions you make. And I think that's sort of a general point, that sort of explicitly modeling the sources of the bias can design specific interventions that sort of maybe allow you to be accurate and maybe also fair. And there's another paper in this conference that has a similar motivation that I think is a really great paper, Bias In, Bias Out. And there's some other related work here, but I don't really have time to characterize that. So that's the end of my slides, and I'm really excited to hear your guys' questions. And I also just want to say, I think it's really great FORC is happening in these wild times. And so, yeah, I would love to hear some questions. And yeah, thank you.
Thank you for that talk. So as always, please ask questions by raising your hand. If you're a participant, or butting in if you're a panelist. You can also type your questions in the Q&A or in the chat.
I see some, wait, okay. All right, well, if there's no questions, I can just sort of talk, or we can end.
There is a question from Robert A. Since it is hard to get access to the true distribution in practice, how would you validate this? Could you use a holdout of less biased data?
Yeah, that's a fantastic question. So sort of our prototypical example that we're thinking about is maybe hiring, where I would say the way you could validate this is you create like a subsample that you can do like really kind of expensive labeling processes, where maybe you want to evaluate whether or not someone is a good job candidate. And maybe the easy source of labels there is like what a manager says about their resume or something. But maybe like I could look at people I do hire, and then I could find better labels for their success on the job. That's a good question. I don't really have a great answer to it.
Okay, then John Roth asks, does your model only consider corrupted measurement of the label, or do you also consider corrupted sampling? I think you briefly mentioned the latter, but wasn't sure.
Yeah, sorry about that. We cover both. So the model I talked about in the 5-minute talk, I mainly talked about what we call underrepresentation bias. So the features are the features of positive examples from group B just don't show up in the data as much. And then also we allow the same underrepresentation of negative examples. And then we also model like biased labeling, which we call labeling bias. So in that case, you should think of like a human labeler looks at someone from group B and is more pessimistic on them. So they're more likely to be given the negative outcome. So yes, we consider both. Thank you.
Great, thank you.
Yeah, thanks guys so much for listening. All right, I'll stop sharing.
All right, and thanks everyone. So that concludes the first day of FORC, and you know, I wasn't quite sure how this was gonna go. Have never run such a large event like this on Zoom, but it went great. And I hope everyone will reconvene with us tomorrow at 10:30 for another terrific day of the program.